So, a seminar on statistical power. What we're going to talk about is what statistical power is and what statistical power might be good for. And so, by the end of this session and after you've done a bit of reading and thinking and perhaps done the exercises that are posted for you on my uni, you should understand the concept of statistical power, know something about the benefits of power analysis, appreciate that there are some serious limitations in the way we think about statistics and statistical power, and you should really be able to conduct power analysis for some common scenarios. Those of you who might wish to do a power analysis for your honours research thesis and who don't have one of the common scenarios that we will talk about in the seminar today should discuss it with your supervisor. We're going to talk about two bits of software that do power analysis. So we can do power analysis in R, but we'll also talk about a free program that is called G-Power, which also does power analysis. And if you learn to drive either of those, you can pretty much do what you like. Although it does rely, as you'll see, on you understanding to an extent the sort of models that you're using. Now, to be able to talk sensibly to you about statistical power, I think it is worthwhile going back to the beginning. I don't have high confidence that many of you will really remember everything you've been taught so far about statistics, so it's probably a good idea to start at the beginning, because all of this presupposes an understanding of the framework of statistical testing that we commonly use. So, I want you to imagine that you're sitting on the side of a hill looking down into a valley, and there's a road that runs along the valley, and as you're sitting there you see two groups of travellers walking along the road. They're designated there by green circles and red crosses. So those are two groups of travellers walking along, and it's very easy to see that the green circles are in front of the red crosses. What happens, however, if those two groups become more scattered? So they're still progressing along the road, but they're mixed up now. So the mean distance along the road for the green circles and the red crosses is the same, but can you now tell which group is ahead of the other group? Probably not. It's fairly arbitrary, I would have thought. Now, we can keep the travellers scattered, but separate them so that there's a greater average distance apart. Now, it's clear once again that the green circles are ahead of the red crosses. It's exactly the problem that we confront in our data. We confront the problem of variability in our data, and to be able to separate signal from noise is why we use statistical tests. So, statistical significance testing. Statistical significance testing requires that we have some hypothesis about something that we're interested in. So, at its most simple, a hypothesis is simply an assertion or a statement about some property of something we're interested in the world. So we're talking about a population parameter. And to decide whether our assertion about that population parameter is true or not, traditionally we use significance testing as a means to decide whether to reject that hypothesis or not. And what we do to test our hypothesis is that we sample from the population that we're interested in. If we were able to measure what we were interested in on every individual in the population, then we wouldn't need statistics. The reason we need statistics is because generally we can't do that. So we sample from the population and calculate a sample statistic, which is the analogue of the population parameter that we're interested in. And if the sample statistic differs from what we specify in our hypothesis, we reject that hypothesis. Otherwise, we continue to entertain the hypothesis. Now, as you're no doubt aware, there is a form of hypothesis testing that centres on a particular hypothesis called the null hypothesis. So the conventional form of hypothesis testing involves a decision about whether to reject or retain the null hypothesis. Now, very commonly, the null hypothesis is framed such that it says that there is no effect, there is no difference, there is no relationship, and so on and so on. I'd like to make it clear to you, though, a null hypothesis doesn't have to state that. A null hypothesis could, for example, state that the correlation between two things was 0.3, and you can collect data and test against a null hypothesis of 0.3. But practically speaking, almost invariably, the null hypothesis is one that says no difference, no relationship, no effect. Now, what's the way that null hypothesis significance testing works is that what you can do is specify a set of values that you would expect if the null hypothesis were true, and you can test your data against that distribution of values. And you can either reject or retain the null hypothesis. If the null hypothesis is rejected, then what's referred to as the alternative hypothesis is supported. Now, this is where we get into a little bit of trouble, because most people think that when they reject a null hypothesis, it supports whatever they really think about what's going on. That's not the case. When you reject a null hypothesis, what you're doing is actually supporting an alternative which strictly is everything that's not the null hypothesis, not what you happen to think is the way of the world. So, an easier way to think about this is in terms of sample means. So what you see represented on the slide there is what's called the sampling distribution of the mean. So the idea of a sampling distribution of a statistic is that it's a hypothetical distribution that represents the set of values that you would take if you repeatedly sampled from the population that you were interested in, calculated the relevant statistic, and then put that sample back and sampled again. And you do that over and over and over, and what you wind up with is a distribution, in this case, of sample means. We can specify what that distribution would look like for the null hypothesis, and it turns out that it will be our old friend, the normal distribution, which has elegant characteristics. It's symmetrical. Its mean is the estimate of the mean in the population. Its standard deviation is referred to as the standard error of the mean, and we can know the proportions of values we would expect at any part of the curve. So we know that values that are close to the mean have high probability, and values that are a long way from the mean of that distribution have a low probability. And this is where null hypothesis significance testing comes from, because we can specify what the distribution would look like under the assumption that the null is true, and then we can set limits whereby we will say if our data is unlikely under the null hypothesis, then we reject the null hypothesis. The values that we typically use cut off 2.5% at each of the tails of the distribution. This is where the 5% level of significance comes from. So when we reject a null hypothesis because our sample statistic falls in those rejection regions, we say that our result is statistically significant with a p-value less than 0.05. And that's the last time you'll hear me ever say p less than 0.05. Now, with this distribution here, the critical values that cut off 2.5% each end, because this is a standardised distribution, are z-scores of plus or minus 1.96. Now, is that all clear so far? It's a game that we're playing, if you like. We're setting up a null hypothesis that we would like to reject more often than not, and the way we do that is by comparing our sample statistic with the values that we would expect if the null hypothesis were true. Have you seen this sort of contingency table before? So this is purportedly how we make decisions in null hypothesis significance testing. So it's a 2x2 contingency table. Across the top we have reality, which is not known to us. But we can be sure that the null hypothesis is either true or it is not. Then we have the decision that we make based on our data. And when the p-value associated with our data is less than some pre-specified probability, which we designate alpha, and which typically or almost invariably is a p-value of 0.05, when the probability associated with our statistic is less than that value, then we reject the null hypothesis. Otherwise, we retain the null hypothesis. And so you can see, if we reject the null hypothesis when the null hypothesis is indeed false, then we've drawn the correct conclusion. We cannot know that, but under this framework, that is what we would have done. If we fail to reject the null hypothesis when the null hypothesis is true, then we've also drawn the correct conclusion. So there are two ways of being right in this contingency table, and there are two ways of being wrong. If we reject the null hypothesis because the p-value associated with our statistic is less than alpha, but in reality the null hypothesis is true, then we've made what's referred to as a type 1 error. Making a type 1 error is viewed very dimly in science because you are claiming that some effect exists when in fact it doesn't. And that means that other people will follow you and continue to work in the area on the basis of a mistake that you have made because by chance, the statistic that you calculated, the sample that you drew from the population, resulted in a value that was very unlikely under the null hypothesis, but nonetheless, the null hypothesis is still true. On the other hand, if the null hypothesis is false and there is an effect in the population, but you fail to reject the null hypothesis, that means that you haven't detected an effect that actually exists. For some reason, that's not viewed as much of a problem in basic science as type 1 errors are. But you can imagine that making a type 2 error, that is, you fail to reject a false null hypothesis, could have quite serious consequences. In medical research, the classic example would be something like, you're working on a cure for some disease and you conclude that whatever it is you're working on doesn't cure the disease when in fact it does, and so that line of research stops because it's seen to be a dead end, but you've actually not detected an effect that really exists. Now you'll see that there are probabilities associated with each of those outcomes in that contingency table. So the probability of a type 1 error is given as alpha. So in some ways that's under your control because you pre-specify your rejection criteria for the null hypothesis. And so you might say, well, to avoid making a type 1 error, I'm going to adopt a really strict alpha level. So instead of 0.05, you might say, I'm only going to reject a null hypothesis if the associated p-value is very small. Why not say p with 6 zeros before you hit a 1? Doing that, though, will sure protect you against a type 1 error, but as we will see, there are trade-offs that we have to make in this process. The probability of drawing a correct conclusion when the null hypothesis is true is simply the complement of the probability of making a type 1 error, 1 minus alpha. The probability of making a type 2 error is designated as beta. And so the complement of that is the probability that we will correctly reject a false null hypothesis. And that is the definition of statistical power. So statistical power is the complement of making a type 2 error, but it's easiest to think about statistical power in terms of the probability that you will correctly reject a false null hypothesis. So, the two types of errors: rejecting a null hypothesis when it's really true is a type 1 error. Failing to reject a null hypothesis when it is really false is a type 2 error. The probability of making a type 1 error is up to us, but by convention is set at a p-value of 0.05. The probability of making a type 2 error is denoted by beta, and power is the probability of correctly rejecting the null hypothesis, which is 1 minus beta. So we say in statistical talk that power is the probability that we reject the null hypothesis when the null hypothesis is false, or that we correctly conclude that there is an effect in the population when that effect exists. So what determines statistical power? The significance criterion we adopt. because, as I say, there is a trade-off. These things are all related to each other. If you set your significance criterion really stringently, then the probability that you will make a type 2 error increases. So you reduce the chance of a type 1 error but increase the chance of a type 2 error. Why is that? Well, this system of power, the alpha level, the sample size, and the size of the effect in the population are related to each other such that if you know 3 of them, the 4th one is defined for you. So it's a system that has only 3 degrees of freedom. Statistical power is determined by the significance criterion you adopt, the sample size that you have, the effect size in the population. And as we'll see shortly, knowing 3 of those things means that we can determine the 4th, and that is what power analysis is about. I just put that there in case I needed it again, but I don't think I do for the moment. Well, yeah, actually I do, because I'm going to show you one that might confuse you. All right, so this is a null hypothesis distribution. So the assumptions, we assume the null hypothesis is true and we can specify this distribution. So that's abstract. Here's an example where we're measuring something, and under the null hypothesis, we are assuming that we have a mean of 4 and a standard deviation of 1. So that's what that means at the top of the slide there. The null hypothesis distribution says whatever we're measuring has a mean of 4 and a standard deviation of 1. And so because it's a normal distribution, that's what the n stands for. It says n is distributed normally with a mean of 4 and a standard deviation of 1. We can draw the implied distribution, and you'll see that it's centred on 4, and 2.5% of the distribution lies in the tails, and we know that in the right tail that the critical value will be 5.96. Like before it was 1.96 in the standard normal because the mean here is 4. So you can see there's a line that I've drawn there just to the left of 6. So any statistic that we calculate for our sample that has a value bigger than about 6 will lead us to reject the null hypothesis. Similarly, a value that was less than about 2 would lead us to reject the null hypothesis. Okay, do you get that? Because that's really important what I'm trying to represent there. Now, when we sample from the population, we don't really know what the effect in the population is, because if we did, we wouldn't bother doing any of this. What if the population that we're sampling from, as opposed to being the distribution at the top, actually is a distribution that has a mean value of 7 and a standard deviation of 1. That's what that distribution would look like. Now, if I've lined that up so that what you can see is that instead of sampling from the distribution at the top, we're sampling from the distribution at the bottom. How much of that distribution at the bottom lies to the right of the critical value implied by the null hypothesis distribution? Well, it says on the slide there, 85% of the real distribution that we're sampling from lies to the right of the critical value implied in the null hypothesis distribution. So that part that lies to the right is the power that we have in this set of circumstances. Unbeknownst to us, we're sampling from this distribution, and we actually have power of 0.85 to detect an effect. So, because we're sampling from this distribution, 85% of the statistics that we calculate are going to fall to the right of our rejection criterion. It also shows that 15% of that distribution lies to the left, and that's the probability of us making a type 2 error. So what you have to appreciate is that even though things are very unlikely, they can still happen. So we could, when sampling from this alternative hypothesis distribution, calculate a statistic which is consistent with the null hypothesis distribution. And that's shown in green there. 15% of the time when we're sampling from this alternative hypothesis distribution, we'll fail to reject the null hypothesis. So you see how these things are related to each other, okay? So that's the basic theoretical stuff about power analysis. How can we use what we've just been discussing? A common use that you almost intuitively will be familiar with is the determination of sample size before you conduct a study. It's called a priori power analysis because it gives it a bit of Latin which says we're doing this before we do the study, prior to the study. So given an effect size, the alpha level that we're going to adopt, and the power that we would like to have, so we've got 3 of the 4 things, we can solve for the sample size that we'll need to achieve that level of power. After we've done a study, after the fact, post hoc, we know the sample size we had, we know the effect size that we found, and obviously we know the alpha level that we used. We can use power analysis to determine the power that our study had. Now, I'm going to talk about that in a little more detail later because it's not as straightforward as that. It's one of the things that people tend to get wrong in using power analysis. Nonetheless, the principle is correct. We know 3 things, we can determine the 4th. The reason that we might do that is what's at issue in the second form of power analysis. It's possible that you have limitations on the size of the sample that you can access. It may be because, like yourselves, you have limited time to conduct research, or it might be because you're interested in a specific population of which there are few members, clinical populations, all sorts. There's all sorts of scenarios where you can imagine that you can only recruit a given sample size. The question that you can answer then is, given that sample size and the power that I would like to have and the alpha level I'm going to adopt, what size effect can I reliably detect? And what I mean by that is, what size effect can I detect such that I'll be able to reject the null hypothesis? And that in itself can be an interesting form of analysis as well. So 3 uses of power analysis. Now, I've sort of glided past the issue of effect sizes. Here are some common measures of effect sizes, some that you'll be familiar with, some not so much. Pearson's correlation coefficient is a measure of effect. It's a measure of the magnitude of the linear relationship between 2 continuous, normally distributed variables. And there are conventions in psychology or social science more generally about how we interpret the size of effects. So correlations of 0.1 are small, 0.3 are medium, 0.5 are large. Those of you who